Cuando quieras.
Vale. Welcome, Luis Sola Conde from University of Trento. He's going to talk about geometric realizations of birational maps. Thank you, Luis.
Okay, thank you very much. First of all, I'm very glad to give a seminar in Madrid, and I hope that one day I will do it also physically in Madrid. Okay. Okay. I'm going to talk about the relation among torus actions and birational maps, and this is part of a project with many people. Lorenzo Barban, Alberto Franceschini, Gianluca Occhetta, Eleonora Romano, Stefano Urbinati, and Jarek Wisniewski, and nowadays also Roberto Muñoz. But the results I'm going to review are included in 3 papers. In these 3 papers that you have seen here, mostly on this one. Okay, but I will also say a couple of things about these 2. The talk is divided in 3 parts. First, I'm going to do a warm-up, and this is, well, say, it's not really an introduction. It's a warm-up in the sense that I'm going to give some, say, visual ideas of what I'm going to do. Then, say, the real talk is divided in 2 parts. The first one in which I will talk about sister actions. Oops, sorry. Oops, like this. Where is it? Sorry, I'm sorry. So the first one in which I will talk about sister actions and the relation with birational transformations. And then I'm going to talk about how to go the other way around, starting with birational transformations and finish with sister actions. So the idea is that the 2 things should be more or less equivalent in some sense. Okay, so for the warm-up, I'm going to recall some very old book that I read, that I was obliged to read when I started studying mathematics many years ago, which is Flatland. If you remember Flatland, the main character was a square living in a 2-dimensional world, and he meets someone from a 3-dimensional world, which is a sphere. And the square, what he sees is, well, a point that turns into a small circle that grows, and at some point it starts decreasing until it turns again into a point and disappears. And and this is of course what happens when a sphere intersects a plane. Okay, so I think you all remember this story. Okay, but so in my version of Flatland, what is happening is that the Mr. Square meets something polyhedral. It meets a cube. Now it's a cube that passes through a plane, and then Mr. Square, what is seen when Mrs. Cube is passing through the plane is, well, first, of course, a point, then small triangle, then an hexagon, then a triangle, and finally a point, and disappears. Okay. So now the thing that I want you to think here is that one of the things that is happening is when you see this triangle, it has 3 faces, and then there are new faces that appear, which are these 3. So the form of the polygon changes, and new faces can appear. Okay. So let's go to the next episode of this flatland. And what we see now, we are in a three-dimensional world. And so our main character now is Mrs. Cube. And she meets this strange character that I call here Mr. T. And what she sees is, well, first a point that turns into a small tetrahedron. And then at some point, the tetrahedron grows until at some point in the vertices of the tetrahedron, a small triangle appears, the triangle grows. So you have to think like these white faces go approach the origin, so go inwards, whilst the yellow faces go outwards. So at some point, what is going to happen is, well, say the size of the faces will change, but at some point, you see this is going to go in this direction, and this guy is going to go in this direction. At some point, they will meet in a point, and then it will we will not change the number of faces, but what is going to happen is that if you look at this, is going to change from this to this. So we are not going to, in this step, we're going to add new faces. In this step, we're going to change to do a mutation on the relation among the faces. Then, so in this step, triangles turn into hexagons and hexagons turn into triangles. And then finally, the triangles disappear and the hexagons turn into triangles again, and we will get again another tetrahedron. And finally, a point. So I think, well, if you think of this in view of this thing, so this is the generalization of this, and this Mr. T is just the tesseract, or the hypercube. And this is what we see. So we have two types of operations. One in which faces can appear or disappear, and then there are these mutations that we may call flips in some sense. While this thing and this thing should be blow-ups. Okay. So now let's talk again about flatland. Well, flatland, I think you all know that, well, if you talk about flatland with a differential geometer, probably he or she will say that, okay, the flatland is Morse theory. In Morse theory, what we study is, if we want to study, well, this is a typical example. I have a donut, and it's the donut that say passes through a plane, or if you want, you have a gradient function on the torus, and then it changes shape. And well, and then you can say reconstruct the torus by looking at what happens when the intersection changes shape. So in the critical points, which are, say, these 4 points here. Okay, so this is the Morse theory, but I'm not going to talk about Morse theory. I'm going to talk about what in complex algebraic geometry, well, it's believed to be say, corresponding to Moore's theory, which is the Bianisky-Virula theory, which is the theory of actions of C star. Okay, so now I'm going to talk about C star actions, but please keep these examples in mind because somehow they will come back in some examples. So now I'm going to talk about C star actions and present some examples. Okay, what is a torus action? Well, the setting is a normal projective variety X defined over the complex numbers and endowed with a C star action. And then what is known is that you have a set of fixed points, which is denoted in this way, which is a union of irreducible components. And the usual notation is if you take a point in X, so we use the subscript plus and minus to talk about the limiting points of the orbit of X. So if this is X here, okay, usually I take t going to infinity on this side and t going to 0 on this side. And this point is going to be X minus, and this is going to be X plus. And these are called the sink and the source. So this is the sink, and this is the source. So they always exist, essentially, because the variety is projective. Okay, now, if I take a general point of the variety, its sink will belong to a certain component of fixed points. Okay, so and that component is going to be called the sink and the source, and the other is going to be the source of the action. Okay, so and I usually denote it by y, capital Y plus and minus. So this is Y minus and this is Y plus. Okay, now there is an interesting thing is that, okay, since the variety is projective, we can put it into a projective space. So by using some very ample line bundle. So let me start with an ample line bundle and L on the variety X. And what is happening is that the action of C star extends to L. This is what is called a linearization of the action. And it turns out that, well, then it extends also to the global sections of the line bundle. And so that, say, for instance, for a sufficiently large multiple of L, you take, so a very ample multiple of L, you will take this guy, okay? And the action in X will pass to the projective space. And the actions on the projective space are well known and are very simple. I think, some days ago, Gianluca Occhetta talked about these actions and gave you some examples. If I have the time, I will present some examples as well of this thing. But essentially, what is happening in the projective space is that the fixed point components are projective subspaces, linear subspaces, and the action is given by on an appropriate basis by monomials. Okay, so well, now once you have the linearization of the action, you can associate to every component a weight. The weights are elements of this of the group of characters of C star, which is isomorphic to Z. These are the morphisms from C star to C star. And these are integers. So these are the exponents. Say, remember that, well, this is what I wanted to say before. If you have an action of C star on Pn, what you will see is this T x0 xn is equal to T2 something times x0 T2 an to xn, if you choose coordinates appropriately. These are the weights of the action on the projective space. And then if you want the weights on X, you have to take just the intersection of of the fixed point components of the projective space with X, and you will get the weights of the action on X. So in other words, the drawing that I have here, it's a restriction on the projective space. You will get some fixed point component of the action on the projective space with some weight. Well, this could be another one in the projective space. It could be that you have some that do not intersect X. Okay. But you will have some weights for which you have fixed point components. So you will get a picture like this. And this defines two numbers. One is called the bandwidth, and this depends on L. It is the weight on the sink, on the source, minus the weight on the sink. Now you also understand why I chose the infinity on the left and the 0 on the right. Because essentially what is happening with the weights is that they grow in this direction. So y minus is, in y minus we will get the minimum weight, and on y plus we will get the maximum weight of the action. So the difference of between these two weights is, it's called the bandwidth of the action. And well, but this is of course, if we change L by a multiple of L, what is going to happen is that essentially we are going to multiply the weights by M, but nothing is going to change. So then, so in some sense, it is interesting to have something that do not depend on multiples. And this is the criticality. The criticality is the number of weights minus 1. It's essentially the number of jumps that you have to do from one weight to the other. So in our notation, the weights will be called A1, A0, A1, AR minus 1, AR, and the criticality is going to be called R. Okay, so, okay, enough about sister actions. Well, there are some concepts associated to torus action. One is the Bioninsky-Virula cells. These are for a fixed point component, x plus minus of y. These are the points such that have the sink or the source in y. So for instance, here I chose this component y, and I took the number of points, the points that converge to infinity to y is this set here. Open on the right. So this thing is not in the Bioninsky-Virula cell. And Bioninsky-Virula in the 70s studied this in the particularly in the smooth in the case in which X is smooth. And what he proved is that this is essentially it's locally isomorphic to the normal bundle. So locally means that on a neighborhood of every point of y, this thing, the Bioninsky-Virula cell looks like the normal, like the normal bundle of y in X. And well, Well, sorry, not exactly. It looks like if you take y, you have the normal of y in x. And the action of C star extends to this bundle, and it divides it into pieces that we call ny plus and ny minus, which are the sub-bundles on which the weights are positive and negative, which essentially the normal is on this direction. Sorry, the normal is on this direction. The negative normal and the positive normal is on this direction. Okay, this is not a global isomorphism, but this is essentially due to the fact that somehow you could have isotropy on some of these orbits. So this tells you that if you have you could have here an orbit on which the action of C star well, is not the natural one but the square. So you have isotropy Z2 and or Z3, whatever. And in this situation, what you will see here is not a vector bundle. Sorry, yes, not a vector bundle, but something that only locally looks like a vector bundle. Or in other words, what is happening is that the transitions will not be linear. Okay, but there is this condition that we call equalized, in which you have no finite isotropy, in which the two things are the same. This is a technical condition, and many things can be done without this equalized condition. Okay, what is important is this. The B-type condition, we say that it is B-type, the action is B-type if the sink and the source are divisors. So on a B-type, every point is the limit of precisely, every point in the sink is precisely the limit of one orbit and no more. Okay, and then there is this condition Bordism that I don't want to consider now. So let me forget about this because it's not important now. But this B type is important. Okay, now let me talk about the geometric invariant theory quotients of a C-star action. So, and well, this is of course due to Mumford, but I think a nice complement in the case of C-star is the work of Wiaunitsky, Virulas, Vienchitska, on which they essentially tell you visually how you can think about the GIT quotients by a C-star action. So essentially, what GIT tells you that you can have some quotients, GIT quotients of the variety by C-star by taking say, well, as before, X L samples, so you can write X as the approach of the ring of sections of L. Okay, and now what is going to happen is that this guy will be divided in weights, in eigenspaces. So we divide it in weights. We put here some value A, I don't know, or well, maybe R. Okay, and you will get something like this. And then you can take subrings that contain, say, that contain some weights in which R is a multiple of something, okay? Some rational number tau. So you choose a rational number tau. This has to be taken in among the possible, in the set of, say, in the interval among the 0 and the criticality. And so essentially you choose here tau, it could be this one, and then you take the subring on which, say, the weights are multiple of tau. Okay, here tau is A divided by B, I put B here and A here, but essentially this is essentially the same as doing H0 ML M tau, okay? So the multiples of tau, and what you will see, okay, then you take the approach of this algebra, which is finally generated, and you will get GAT quotient of the variety. Now, what is it exactly? So if I look here at tau, Bialinski-Virulas-Vinchitska tells you that, so for this tau that I have in my picture, I have to take out all this part and this. So, and then I will look at all the orbits that are not contained there. So essentially, I'm like cutting here and look at all the orbits that pass. They could be orbits like this. They could be orbits like this, okay? But I'm not counting the orbits like this. So I'm taking out these orbits and these orbits. If I take tau here, then I'm like slicing my variety, my picture like this, and I'm looking at all the orbits that are not contained here or here. So I'm taking this thing out. Now, there are two possibilities. Either tau is a critical value or it is not. If it is a critical value, then I will get a semi-geometric quotient, because I will take out this part. For instance, if I take tau, this one, say take this tau, then I'm canceling out this thing and this thing. Okay, here there is nothing, just the sink. And I'm looking at all the other orbits. So in particular, I have these orbits and these orbits. But since they have a limiting point in common, they go to the same point in the semi-geometric quotient. So these two orbits go to the same point. All these go to the same point. Okay, so this is a semi-geometric quotient. If I instead take another tau doesn't correspond to a critical point, then I will get a geometric quotient of the variety. Okay. Now, what is also nice is that the tau doesn't depend on, well, depends only on the interval that you are taking. So if you move your tau inside of the open interval, you will get the same variety. So our notation is for the semi-geometric quotients, GXII, okay, corresponds to the critical value AI. And if I take a tau inside an open interval, then we call it GXII plus 1. So if this is AI and this is AI plus 1, if I take tau here, this quotient will correspond to will be called GXII plus 1, and this quotient will be called GXII. Okay, so say we imagine it as some slicing of the variety, but this is not, well, this is complex algebraic geometry, so we are not really slicing, we are not cutting with something. Okay, what is going to happen later is that in the particular case of toric varieties, this is going to correspond to some slicing. but I will get to this later. Let me see this example. Okay. No. Let me talk about induced birational transformations. So now I have here I have the picture of some variety with a sister action of criticality 3. So it has these 4 fixed point components. And so you have 4 possible semi-geometric quotients, which are these 4. And then you have 3 geometric quotients, which are these 3. And then you have the maps like this. These maps are induced by the fact that what I told you before, these are quotients of some open sense on the variety. So then we just send orbits so the image of an orbit to the image of an orbit. So what is happening, look for instance what is happening here. So what is happening here is that in GX01, all these orbits, let me show it to you like this, all these orbits are different, okay? When I map it to GX00, since now they have a common point, some of them have some common point, they contract. So here you will have some, you will contract something. In fact, this thing here contracts, say, this will be a fiber type of contraction. Okay. Now, if you look at what is happening, also when you pass to GX11 from GX01, you are contracting orbits like this. If you have this orbit and this orbit, they have the same limiting point, so they go to the same element in GX11. So you have some contraction. But now this is not in general fiber type, but this is a birational contraction. Okay. And so on. And here you have some birational maps. Okay. I will show you some examples of this thing. The first and most stupid example, okay, if I am able to, okay, it's the case of P1 times P1 times P1. This is, and the action of C star is the, say 3 times the natural action. So this means that if you take T here, if you take T times x0, x1, y0, y1, and z0, z1, this is x0, tx1, y0, ty1, z0, tz1. This thing is called the natural action on P1. Okay, so it's the one with that has a sink and source, the north and the south pole. So if I take this action, let me call it the diagonal action. This is going to have 8 fixed points of coordinates infinity and 0. So you have these 8 points. Now the sink is the one that has 3 infinities. It's infinity, 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 and the source is the one with 3 zeros. Okay, and you have some points in between. And the obvious way of representing this is with a cube. Okay, this is what this picture is meant to. So this, you have to imagine this as a cube. Now, what you have now? You have 3 ways of cutting, 3 geometric quotients. The first one is going to be P2. by symmetry, the other one is P2. If you want, for instance, to see the first P2, you have to think that in this point, well, this action is equalized. The Bianitsky-Virula cell is like the normal bundle, which in this case is the tangent bundle. So the tangent bundle is C3, and then you have to divide C3 by the homothety action, so it is P2. Okay, now when you go to the second geometric quotient, which is this one, oops, I'm sorry, which is this one, what is going to happen is that you will get an hexagon. This is the del Pets of degree 6. Okay. This is going to be a blow up. These are blow ups. And this map is the Cremona transformation. The standard Cremona transformation. So this is what is happening. And this resembles the second flatland picture that I had. Okay. And so let me, okay. But you can say, okay, yeah, that this is just because you painted it with a cube. Okay. Let me go to the next one, which is the case of P1 times P1 times P1. I take the same action. And what I get essentially is the first quotient is P3. The last is P3. And here I have, this is P3 blown up in 4 points. This is P3 blown up in 4 points. And this thing, this map, is the flip of six lines. Okay. Now, and if you paint your P1 times P1 times P1 times P1 with a cube and you slice it, what you will see is this picture that we had before. So what is happening here? What is happening here is that here we are dealing with toric varieties. So the toric varieties are represented by polytopes. Okay, so let me see what is happening when you consider sister actions on toric varieties. Okay, so if you have, okay. So what is a toric variety? Well, I think you know this thing. A toric variety is is the closure, a projective toric variety is the closure of a torus, a complex torus, so a C star to the n, on a projective space. So the image of a torus on a projective space, and then you take the closure. And it is usually denoted by X sigma, where sigma is some fun on some vector space endowed with a lattice. Okay. The important thing is this. If I take a very ample H invariant divisor, it will give me an embedding of this variety, and what you will see, if you want, is this. You will take H, you will map it to some projective space, and by means of, here you will have T1, Tn, elements of the torus, and then you will do some, this is called T, you will take some monomials. Okay, this may be N. You will take some M plus 1 monomials. Look in MH, okay, times R. MH is the set of characters of the torus. For every monomial, you will get a point, okay? So this is M0, M1, Mn. And you will get the set of sections that you will be using to do your to construct your toric variety as a closure is the intersection of a polytope with of your polytope with the lattice. So the lattice points of a polytope. So this is the general theory. And you can say, okay, what is happening? Why can't you just forget about some of these lattice points? So why don't I take just some of the points inside of this polytope? Okay, because I forgot to say that I'm considering normal projective toric varieties, and the normality tells you that I'm taking all the points in the polytope. So to consider a toric variety, a projective toric variety is essentially equivalent to consider some polytopes, lattice polytope in this space here. So this represents completely my variety. Okay, now what about some C-star action? Okay, if I take a C-star action, okay, here I'm taking C-star containing the maximal torus. Remember that MH is the homomorphisms from H to C-star. And so if you take this inclusion, it corresponds to a map from MH to Z. Now, if you tensor with R, what you will get is a linear projection from MH tensor Z R to R. And this is where your polytope lives. So you will, sorry, P of L. So your polytope lives there, and you are projecting it to some line. Now, like this. So this could be my polytope, the cube, and I'm projecting it to a line. Okay, now the general theory tells you that the GAT quotients of your toric variety will be H divided by C star toric. So the torus H divided by C star will act on the GAT quotients, and the polytopes associated to these quotients will build the slices. So if I take this value, you will get this quotient, and this quotient. Now, the cube corresponds to P1 times P1 times P1. If you slice it properly, you will get triangle, two triangles and an hexagon. And they correspond exactly to the case of P2, the delpets of degree 6, and another P2. So what I'm saying is that these pictures that I had here, okay, that I got, say, intuitively, correspond to the GAT quotients of these varieties as toric varieties. So we can use this thing. Okay, I'm going to forget about this example 3, okay? And I'm going to go to talk about these geometric realizations of birational transformations. Let me recall this thing. I started with a C-star action on a projective normal variety, and then I took a linearization on an ample line bundle. So I got this action on the pair XL. And then I said, okay, it gives me some GAT quotients, some geometric quotients that are birational equivalent. Okay. Now, say the language that we use is, we are interested in these birational maps. And we say that the variety endowed with a sister action is a geometric realization of the map psi. Okay. So it's like we now we want to start with a birational map, and we want to construct a normal variety and dot with a sister action, such that the birational map that it induces is is the one that we started with. Okay. Now, these geometric realizations are not unique. For instance, start with this variety that you have seen already 10 times, okay, with the inaction of C star. Now, and let me think that the action is equalized. Okay, so that the orbit, you don't have isotropy. Now take this guy and blow it up. Since this is H invariant, torus invariant, then the action will extend to the blow up also the source, and the action will extend to this. And what is going to happen is that when you blow up here, you will separate all these curves here. So you will get a divisor, which will be in the new sink, and then every point will be the limit of a single orbit. So this is B type. Now, the geometric quotient here and the geometric quotient here are the same. And the same here. This is, so here the GX01 and here the GX01 are the same. And the same with the R-1 R. They are the same. Okay. Now I have to warn you that if the action is not equal, here I'm thinking of the case in which X is smooth and the action is equalized. Then the operation that I'm doing here is the blow up. If those conditions do not hold, then this is not smooth blow up. This is some kind of locally toric blow up. It's not exactly a blow up. Okay. So, but such operation exists. I will tell you later why. Then you can say, okay, what happens if I blow up something inside? So if I blow up an inner fixed point component. And this is what I did here. Here I started with this B-type geometric realization. So this B-type action here. And then I took this component and I blew it up. And I introduced this new divisor. And now what is going to happen is that, again, the first and the last geometric quotient are the same because I didn't change anything there. Okay, so the map, we will get another realization of the map. So geometric realizations are not unique, but because you can do this, you can perform this birational operation and change it. What is really happening? What is really happening is that if you now think that in between these two, I have another geometric quotient. Okay. Here, this map decomposes into two birational maps. And here instead, I have, say now, okay, the polarization is not the same, but I have a geometric quotient here. Okay. And a geometric quotient here. So the map is the same, but I'm factorizing it in two different ways. So this is like, say, here, what is happening is that my map was, say, let me call them these quotients simply G0 and G2, okay? And here I had G1. Okay, what I'm doing here is I'm taking, I will have okay, because another one here. This will be a blow up, and this will be a blow down. And then I will be factorizing it like this. Okay, so somehow the geometric realizations come with a factorization of the map. The interesting thing is that if we are careful enough, these geometric realizations are simple. So these factorizations are simple. And this is what I'm going to say in a second. So let me put some order on the material that we have with this concept of pruning. So the pruning is, I start with a normal predictive variety with a sister action. As usual, I write my varieties, the predictivization of some finally generated algebra of sections of L. And then what I'm going to do is I'm going to cut the my variety. I'm going to say cut the ring. 1 second. Yes. Maybe I can copy this guy, or I can. Okay. So what I'm painting here is X. This is X. Then I'm going to choose two values, rho minus and rho plus. Some integers will be something will give me these two values here. Okay. And then what I'm going to take is I'm going to take all the sections whose weight is in between these two values. Okay, since I'm taking multiples of ML, so I'm taking elements that have the weight in between rho minus and rho plus. So, and I'm going to take the approach of this. What I'm doing is I'm essentially cutting like this. Okay. So, you can prove easily that this variety that we call X rho minus rho plus is birational equivalent to X, and that it inherits a sister action, so that the birational map is sister invariant. So, and okay, and that what is happening is this: if I take, imagine that the critical values are A0, AR, and I'm painting it. These are these values here. And I take rho minus in the first interval and rho plus in the last open interval, okay? And I do the pruning. Now, so it is what I'm trying to represent here. So this is the first, and this is rho minus, and this is rho plus, okay? What is happening is that now the new sink of the variety will be this quotient, the first, and this will be the source of the action. So I will get something like this. I'm substituting this by this, by the GIT quotient. So this is like the sister invariant blow up. If X is smooth and the variety is, and this action is equalized, this is just a blow up. In general, it is not. So it is slightly pure general than a blow up. Or you can call it blow up, or I don't know, sister equivariant blow up. I don't know how to call it. The thing is that you can cut even further. And okay, first of all, that for instance, I could cut here, okay, and I would get only this part here, okay, or I could even do, okay, important is that, as in with the GAT quotients, this way of pruning, it does not depend on the particular value on an interval, but on the open intervals. So if I take this and move it slightly here or there, it will not change. Okay, I will get the same thing. In particular, if I do something like this, okay, now I will not have inner fixed points. And this, the sink and the source will be equivalent, and there will be exactly one orbit going from here to here. So this will be a P1 vibration with two sections. If the action is equalized, this is going to be a P1 bundle. Okay. Now, there is here one, say, technical step, which is, okay, this is the pruning. And there is a theorem that tells you that, well, when I take, but like this cutting on the left or on the right corresponds to taking sections that have some multiplicity on the sink and the source if the action is B-type. Okay, so you have here, so you take this thing, sorry, this vector space is the same as the sections of ML that have some multiplicity on the sink and the source. If you think of it projectively, this is like doing some projection, okay? The projection from the infinitesimal neighborhood of y minus or y plus, okay. But you take this, and now you look at this minus and think, okay, I can also put a plus, okay? If now I take the direct sum of this, and I construct another algebra. So this is like reverting the process. So if you want, I'm starting with this variety. Then I do this pruning process with the plus that I did before, and I can move this thing again to that side or to the other side, okay? So it can be reverted. And this is interesting because the smallest, so you can start, as I told you before, the smallest prunings are P1 bundles. So you could start with a P1 bundle with two sections, and then you can do unpruning and construct a new variety with a sister action. Okay. Now, as I told you before, I'm all the time thinking, okay, I'm cutting like this, my picture. In the case of toric varieties, this is correct. This is exactly what is happening when you consider the polytopes. So for instance, if I take my cube that corresponds to P1 times P1 times P1, pruning corresponds to taking out a piece of the polytope, okay? As well, toric geometers know that the blow-up corresponds to this truncating process. So let me tell you what is happening. Imagine that you have this slice, okay? That you take the pruning like this. What will you see? What you will see is, you will see a prism with bases are two hexagons. And this thing will have exactly, will have 6 faces, okay? Which are the faces of the cube. When I unprune it, I will get the cube again. Okay. Okay. So this is what we do. And we prove in our paper, in this paper that I told you before, I proved this thing. This is Barbani and Occhetta. We start with a birational map between two q-factorial birational contractions of a Mori dream space. Then we prove that there is a geometric realization that is a Mori dream space. Okay, a geometric realization of the action that is a Mori dream space. There is this word chart here that it is not really important. And okay, and if you think about, I will explain this statement in a minute, but let me tell you this. What is happening here is the following. On one hand, we have this map y minus y plus. There is this Sarkisov program that essentially factorizes, studies the factorizations of this map in, say, in Sarkisov links, okay, which are simple birational transformations such as flips, blow-ups, etc. Okay, when you do the geometric realization, this Sarkisov program turns into studying some minimal model program of the geometric realization. So this is the goal of these ideas, is doing these things. And what is also important is that in the case of toric varieties, you can construct the geometric realizations using the computer in a very easy way, okay? Because everything boils down to working with polytopes and learning how to do this unpruning process in general. So here, and this is, I think I'm out of time, but if I can have a couple of minutes, let me tell you about one example. This is the example of an example by Batirev, the number 33 of its list of smooth fan of fourfolds, toric fan of fourfolds. And this has Picard number 3. This is why we chose it, because Picard number 3, we can still paint it. And if you look at its effective cone, it will look like a triangle. It will have 6 chambers. This one is the Neff cone. So here there is Y. Then this Y will have 2 flips, Y1 and Y2. And then we will have 3 divisorial contractions of these guys, say Y prime, Y1 prime, and Y2 prime. So this is a divisorial, these are divisorial contractions. And these are flips. So you have something like this. And these 2 maps are flips again. Okay. Now we want to consider geometric realizations of, say, we want to take 2 elements here. For instance, I chose these 2. And I want to construct some realizations. For instance, I take Y2, I take a polarization here and a polarization here. And I construct this guy. Okay, I take this, I draw this this line here. I take 2 elements here. Okay, 2 polarizations here. I will construct a T1 bundle. So say I take A and A plus H. We take P of A, this is over Y, A and A plus H. Okay. This is a P1 bundle. It will have a natural sister action acting on the fibers. And then I do some unpruning on the left and on the right. And the unpruning now, it will move this to here and it will move this to here. Now, what is going to happen? It's going to happen that now, at some point, I will arrive to, this is y1 prime, and this will give me y2 prime, and it will factorize the map as y1 prime, going to y1, then to y, then to y2, and then to y2 prime. So this is what is happening here. When I say follow this route. If I take instead these two polarizations, A1 and A2, this is simply a flip and another flip. Here, this is a blow up. This is a blow down. And these are two flips. So you can follow here. One is this route. And the other is this route. Okay, and 30 seconds. This is all constructed with, you can construct everything using the computer, as I told you. We have some scripts written and shared in GitHub. So if you want to have a look, you can. I can give you the link to this. So using this guy, we will get, we introduce Y and the polarizations A1 and B2, and what we'll get is, well, it will tell you the combinatorial data of the variety. It will tell you the factorization, what it's doing. For instance, this is A1, B1. It tells me that it is the composition of two flips. Now, this is for toric varieties. In the case of Moridian spaces, if you know it for toric varieties, since every Moridian space can be embedded in a toric variety, you can use it to extend the theory to Moridian spaces in general by fixing some what is called the Mori embeddings. Okay, and I think I'm going to stop here. I wanted also to present an example of this thing, but let me stop here and because I'm out of time.
Thank you, Roberto. Thank you very much. Are there any questions in the audience?
Well, I don't want to repeat the question I made to Gianluca, so I will change it a little bit. Did you consider the same kind of thing, changing your action? I asked Gianluca about higher dimensional tori, but maybe you can change C star, for example, by SL2 of C, which has inside C star.
Yes.
And it has limits. Is it possible to extend this theory to some other groups, like this, for example?
Well, first of all, let me note that Bianitsky-Virula studied some of these SL2 actions, for instance. Mm-hmm. So what is happening, if you consider SL2 actions, it is that, well, how do you study SL2? SL2 essentially is C star and the Weil group, which is set 2. So what is going to happen is that what you will find, you will have objects that have some set 2 symmetry. It is possible. And say, you will get, and we use this thing at some point when we use these things to prove some say weaker form of Lebrun-Salomon conjecture. So besides the weights and the components, you will have some set to action. So sorry, set to action that say you will have this symmetry here. This is what is happening. And this is very strong because, for instance, this tells you some things about the normal bundles. So the normal bundle here is essentially the same as here, and this decomposition is the same as this decomposition when you revert it. So this is what is happening, and the things are even more stronger if you consider the action of larger groups. If you, instead of C star, you consider C star to the R, you consider a group SL R+1, then you can use the symmetries a lot to study properties of the possible C star subactions of your variety. Yes, this is a general theory. I don't know. But this can be used in many examples. For instance, for the recognition of homogeneous spaces, this idea is very, very interesting. You would look for symmetries of the data regarding the action of a torus.
Okay, thank you.
Thank you very much, Roberto. Are there any more questions? Let me check the YouTube channel. There are no questions in the YouTube channel. I think we can thanks the speaker again and dismiss the session. So thank you, Eduardo.
Thank you.
Thank
Thank
you.
very much, Luis.
Okay, I finished
Okay.
the YouTube emission. Can I ask you a question?
Yes.